Okay, we're going to skip around in the book here just a little bit. I'm going to go to 1.6 before I do 1.5. So, limits involving infinity. All right, first note here, infinite limits. All right, we've already seen that sometimes when we take a limit, we get infinity or negative infinity as an answer. So check this one out here. The limit as x approaches 0, so here's 0. Of course, we know the function is undefined at 0, but as we approach from the left, we had seen this in a previous example that the y value, or value of the function, gets arbitrarily large and starts approaching infinity. We could start stepping closer and closer, and that value of y just keeps getting bigger and bigger. Also, when we approach from the right side, same sort of thing happens. We start getting closer and closer to positive infinity. So our answer in this case would be positive infinity, because the limit from the left and the right were both approaching positive infinity. That is referred to as an infinite limit, meaning that the limit was infinity. Here's another one. Here we're trying to find the limit as x approaches 0 of 1 over x. Again, at 0, the function is undefined. However, as we approach from the left-hand side, our function's value is headed to negative infinity. As we approach from the right-hand side, our function's value is headed to positive infinity. That means from the left, we go to negative infinity. From the right, we go to positive infinity. Since negative infinity and positive infinity are not the same, we would say that this limit does not exist. Remember, we have to have the left and right be the same for us to be able to say that the limit exists. So we get D and E for that one. All right, now how is this infinite limit connected to what we call the vertical asymptotes? In college algebra, we studied vertical asymptotes, and now we have a new definition. The line x equals a, that's a vertical line, is called a vertical asymptote if the function of the function y equals f of x, if any of the following are true. The limit as we approach a from the left is infinity, as we approach a from the right is infinity, as we approach a from the left is negative infinity, as we approach a from the right is, negative infinity, and or if the limit from the general limit without left or right is infinity or negative infinity. If any of these cases are true, then we have a vertical asymptote at x equals a. From now on, I'll be using VA to represent vertical asymptote. So let's take a look. Here, again, it's the 1 over x squared. We knew that that limit was infinity. X equals 0 is a vertical asymptote because as we approach 0, from the left or from the right, we get infinity as an answer. So this dotted line is our vertical asymptote, x equals 0. Again, on 1 over x, as we approach 0, we said the limit doesn't exist, but x equals 0 is still a vertical asymptote because as we proceed to go from the left, we get negative infinity. That's enough right there to say vertical asymptote, but we also have from the right positive infinity, so x equals 0 will be a vertical asymptote for this function also. Here's another one. So take a look at this one here. The limit as x approaches 2, so here's 2. As we approach from the left, our function takes off to positive infinity. As we approach from the right, our function is actually headed towards some number. But all we need for vertical asymptote is for one of the sides to be approaching infinity or negative infinity. So from the left, we have, where is it right here? From the left side, we approach 2, we get positive infinity. As we approach from the right side, it's 1, but we don't really care. This condition right here satisfies what it takes for a vertical asymptote. So we call x equals 2 a vertical asymptote, although the limit doesn't exist there. So you can show the vertical asymptote right here. It's that vertical dotted line. All right, do not confuse the next concept with infinite limits. Now we're going to talk about limits at infinity. So don't confuse these two. Limits at infinity. So far we've studied limits when we let x approach some number a. And we approach it from the left or the right, or we approach it both sides at the same time. Now what we're going to do is we're going to let x approach infinity instead of a fixed number a, or negative infinity. Here's the notation we'll use. Limit x approaches infinity of some function, or limit x approaches negative infinity of some function. So now we're going to let x get arbitrarily large in the positive direction or negative direction. So let's take a look at this here. So what we're going to do is we're going to let our x here approach infinity. So here all I've done is I've shown you the function's value, all right? And you can see here the function's value is 1. I'm going to zoom in so you can really see that. We're looking at the 1 over x function. So what's happening as x gets big? Well, as we start to move down the graph, you can see as x gets big, the function's value is starting to get small. And as we keep going, look what's happening to that value of the function. It's getting smaller and smaller and smaller and smaller and smaller and smaller. And I stopped at 200, but we could keep going out to 2,000 if we wanted to, or 2 million, it doesn't matter. But as x gets bigger, this fraction gets smaller. So the function seems to be approaching something. The question is, what is it approaching? Well, in this case, it's approaching 0. Does it ever get there? No. But the limit is all about what's happening as we get closer and closer to something. So what we'll say is as x approaches infinity, the function 1 over x approaches 0. Approaches, okay? Even though there's an equal sign here, this is in the limit, this is all about what's happening, what's the behavior. All right, let's take a look at the same graph, but now let's approach negative infinity. So now we're going to be letting our x values go out this direction. As we start to go out that way, let me zoom in here. You can see that my values are negative, but they're going to start getting smaller and smaller and smaller and smaller. And again, they are approaching 0. But they're approaching from the bottom of the x-axis instead of the top, like in the previous example, but still getting closer and closer to 0. So we would also say here, and I left out the negative, that this limit as x approaches negative infinity of 1 over x equals 0. All right, so here's an important property of limits, for specific power functions. If n is a positive number or positive integer, 1, 2, 3, 4, so on, then 1 over x to the n, the limit as x goes to infinity or negative infinity, these all go to 0. So what I've done here is I'm going to have a couple of graphs here. We can see what happens to them as x goes to infinity. Right now I'm using a power of 1, so this is just 1 over x. So as I go to positive infinity, the graph gets closer and closer to 0. As I go to negative infinity, the graph gets closer and closer to 0. So the answer is 0. If I make this x squared on the bottom, same thing happens. Approaching positive infinity, it's headed to 0. Negative infinity, it's headed to 0. 1 over x cubed, same thing's happening. Headed towards 0, headed towards 0. And I'll just go out to, let's say, 8. So you can really see this. It's going even faster. So that's what this property is saying. Anytime we have 1 over x to a power, and that power is a positive integer, then that limit definitely has to go to 0. Okay, so here's an example we'll do in class, or 2 examples we'll do in class. One of them will let x go to infinity. Same function will let x go to negative infinity. And we'll see there's a special algebra involved in this problem. Next example, same thing we'll do in class. Next example, again, we'll do in class. There's going to be a lot of algebra involved in that. And then for each of those problems that we'll do in class, there's pictures that we can look at to verify our answers. But we'll do that in class. Okay, so how is the limit at infinity connected to the horizontal asymptote? So here's what we have. Horizontal asymptote was in college algebra. It's a horizontal line that our function is headed towards. That line, y equals L, a horizontal line, is called a horizontal asymptote. If, as we head to infinity, our function approaches that line, or as we head to negative infinity, our function approaches that line L. So we'll abbreviate HA for horizontal asymptote. And so from this problem right here, I have a function. We can see that y equals 1 is a horizontal asymptote because as we go out to the right, as I approach infinity, right, it's getting closer and closer and closer to the value of 1. Right, so that's the idea, is that dotted line that I'm approaching but never really getting to is my horizontal asymptote. I like to look at horizontal asymptotes as being kind of like magnets. They kind of like pull your function towards them, but you never actually necessarily get to that line. We also have, let me see, do I do this one the other direction? I don't think so. It's a different example. So here we have a familiar function. We did this way in the beginning, sine of 1 over x. But now what we're doing is we're letting x go to infinity, and the answer here is going to be 0. So as we go, of course, it was all squiggly in the middle, but we're not headed towards 0 now. We're going to infinity, so we're actually going to go out to positive infinity this way. And you can see I don't show a whole lot. There, I zoomed out a little more. You can really see that it's starting to go towards 0. Also, if we were to go to negative infinity, you can see the same thing. And we'll verify that algebraically in class, determining like why it is 0. But the graph supports our answer. All right, limits at infinity. So here's another one. You can see here that we have sine x over x. We already had studied this one as we approach 0, but now we're going to go to infinity. You can see it's going like this. It's oscillating here. But if I zoom out, you can really see that oscillation, but they're getting smaller and smaller and smaller and smaller and smaller. This is headed towards 0. It's actually going up and down, above and below 0, but it's just getting closer and closer each time. It's like the amplitude's getting smaller and smaller. So this limit will be 0. And this is an important concept. Again, I'll cover in class, like how is it that you can get this answer 0 without knowing what the graph looks like. All right, last note here. So the general idea of the limit, anytime you do a limit, a lot of times you have certain forms that come out. And this is just kind of a summary of those forms and what you have to do when you see it. So if you take a limit, this is important. Suppose when you take a limit of a function, you get the following. If your numerator is headed towards 0, and your denominator is headed towards 0 also, so you're taking the limit and the top and bottom both go to 0, then you must do some sort of algebra to determine the answer. Same thing with if you head towards infinity on the top or bottom, either positive or negative, doesn't matter. Anytime you have some sort of infinity over some sort of infinity, you again must do some sort of algebra to determine the answer. There's not like a quick just, oh yeah, it's this. We have to do some work to get to those. But if your numerator is a constant, like let's say the number 4, and your denominator is going to 0, then what's happening is that the ratio is getting huge, it's getting large. The denominator is getting small, the numerator is staying fixed, and so you are either going to get positive or negative infinity from that. And it'll all depend on, the problem itself, whether or not you're going to get the positive or negative here. I'll do problems in class, so no worries there. If your numerator is headed to 0 and your denominator is a constant, so it's this flipped over, then your answer is 0. So it's like the top's going to 0, but the bottom's stuck at 4 or 10 or pi or whatever. Then what's happening is that the fraction's getting smaller because your numerator's getting smaller. All right. If your numerator is a constant and your denominator becomes infinitely large, then this ratio gets small. So let's say 1 over x, right? X gets infinitely large. 1 over x heads to 0 as x goes to infinity. So we've seen something like this, but let's just remember it as constant over infinity is going to go to 0. If we have it the other way around, infinity over a constant, then we're going to have either positive or negative infinity for that answer. And then the last thing is if your numerator is bounded and your denominator goes to infinity or negative infinity, the answer is 0. And I'll illustrate that in class. That's very much related to this problem here because our numerator sine x is bounded. Sine x is always between, it oscillates. It's between 1 and negative 1, 1 and negative 1. It's going up and down. It's bounded though. The biggest it can be is 1, the smallest is negative 1. But your denominator is becoming infinitely large. And so anytime you have something that's bounded over something that's becoming infinitely large, this last form tells us that the answer is 0.